Hello, welcome to Biochemistry Simplified. We are here again. This is coming to you from our YouTube channels, Biochemistry Simplified from Dr. Elik, and we'll just continue today with titrations and buffers. So we'll continue with titrations and buffers, and to get into titration, we want to quickly make some quick recalls on weak acids, and we say that weak acids uh, we said that weak acids, there's a general reaction for weak acid, which includes HA, the generic form of the weak acid, plus water, and that gives you this reaction right here, H hydronium ion plus A minus. So A here is generic. It is for any species. A could be anything. So in this reaction, as you can see here, what you have in solution is the hydronium ion, which is the same thing as H plus. Remember that we said that this hydronium ion here is same as H plus, or your proton. So if we are to rewrite that reaction in solution, we could write HA to give you H plus for the dissociation reaction plus A minus. Okay, so for weak acid, most of the acids do not dissociate. Most of the equilibrium, this equilibrium that is shown here, is in the reactant form. Just a little is dissociated by the donation of a proton, but more of the weak acid is in this reactant form, and that is why the Ka for weak acids are really small. They mean that it does not go very far forward in the reaction, and that is why most of them are in the reactant form. The reaction does not go very far forward. So if we take that reaction equation again, like I wrote earlier, we have HA plus water in solution, HA signifying the weak acid, and you have your forward reaction and your backward reaction, and you have your hydronium ion H3O plus plus your A minus. So if we look at the acid dissociation constant Ka, we will see that in doing that constant, we have the product, the concentration of the product, okay, at equilibrium will become H3O plus multiplied by the concentration of the species over the concentration of the reactant, of which here the reactant is what? HA. Water there signifies is in solution, and this equation actually is shown at equilibrium. So it's the Ka equation at what? Equilibrium. At equilibrium. Alright, so if we have to rearrange this equation right here, we could make the proton, which is represented here by H3O minus. I told you earlier that it's same thing as H plus. So if we want to make that the subject of the formula, we write, let's rearrange the Ka equation. The Ka equation, in which here the concentration of the hydronium ion is equivalent to your hydrogen ion. So in rearranging that equation, we'll have your H plus concentration is equal to Ka concentration Ha, okay, divided by concentration A minus. Okay, so next thing you will do here after getting this equation is to take the negative log of both sides. Now we have concentration of the hydrogen ion in as the subject of the formula. So you take the negative log of both sides of the equation, and that will give you the following. I'll do that on the next page. Okay, so we are taking the negative log from where we left off. Here's my pen now. Okay, I'm here. So it's taking the negative log, taking the negative log of both sides of the equation, of both sides of the equation, you have so if we take the negative log of both sides of the equation, we will have negative log H plus is equal to negative log Ka plus negative log concentration Ha over concentration A minus. Concentration Ha over concentration H minus. So you see we've just succeeded in expanding that. So what happens here is the multiplication principle, where multiplication is equivalent to addition. So the properties of logarithm was used to expatiate that Ka equation, of which the hydrogen ion concentration was made the subject of the formula. So the negative log of hydrogen ion concentration is equal to pH. Remember that we recall that we said that pH is equal to the negative log of what? Hydrogen ion concentration. And right here we are having the negative log of hydrogen ion concentration. So if we are to rewrite that with pH in mind, we'll have pH, which is a negative log of hydrogen ion concentration, is equal to negative log pKa, which becomes pKa. Remember in our previous, I would say it could be P anything, okay, minus log concentration Ha divided by concentration A minus. So in other words, the acid form over the conjugate base form. So if you remember our last class, we said that in that reaction you have the acid form, which is what gives the proton, and the conjugate base, which is the remnant of the reactants at the product end. So what we have here is concentration of the acid form, negative log of the concentration of the acid form over the conjugate base. So it can be left as this. However, generally, we don't leave it like that. We tend to perform some plus signs, and that plus sign simply means taking the reciprocal of the reciprocal of this. So when we do that, so we write taking the reciprocal of concentration HA over concentration A minus. That changes immediately, though this sign, this minus sign, taking that reciprocal of this automatically changes this negative sign to a positive sign. So when you take the reciprocal, what you automatically have is your pH is equal to your pKa plus, okay, reciprocal will now mean A concentration A minus comes up and concentration HA goes down, numerator and the denominator. And this here represents, this concentration A minus here represents what? The conjugate base. It represents the conjugate base. Why this HA here, of course, is your acid, that is the reactant that gave out a proton. So the whole of this relationship here, pH is equal to concentration A minus, which is the conjugate base, over concentration HA, which is the acid, is known as the Henderson Herzberg equation. Henderson Herzberg equation. So we succeeded in showing you how we get the Henderson Herzberg equation. So this is a very, very important equation right here. This equation, pH is equal to Ka pKa plus concentration A minus, which is the conjugate base, over concentration HA. Very, very important equation regarding acid, bases, and buffers, as we'll see. So we'll do an elaborate discussion on this equation once we start talking about buffers, and we'll do some example problems so that, or example questions, so that you will see how it really flows and work. So next, we'll be talking quickly on titration. So I'll see you on the next slide. To start with, begin with talking about titration, we want to quickly put down a relationship between the pH and the pKa and the concentration of the conjugate base and conjugate acid. Actually, this is what titration is actually all about. So I'll just quickly put that equation clearly here, because it's the basis of which we conduct titration. So plus log concentration A minus over concentration HA. And we said that the concentration of A minus is the conjugate base, and the concentration of HA is the acid, which is the reactant. Excuse me. So the what this equation shows is in a weak acid solution. In a weak acid solution, it actually shows the relationship between the pH, the pKa, and the concentration of the conjugate base and the acid, and it's expressed by the equation above, which is this particular equation. So I'll just quickly want to state that down so that you do not forget. This is very key. So note that the Henderson-Hezibach equation all right, shows the relationship between the pH, shows the relationship between the pH, pKa, and the concentration of the acid, that's the weak acid in reactant, as well as the concentration of the weak base, of the conjugate base rather, concentration of the conjugate base, the concentration of the conjugate base. All right, so that's, and is expressed by this Henderson-Hezibach equation above. All right, so the hydrogen ion concentration, the Ka, the conjugate base concentration, which is A minus, and the acid concentration, they are all present in this equation. So if you have this equation and you have three of these parameters, say you have the pKa or the pH, or you have concentration of the conjugate base or concentration of the acid, and you are left to find just one parameter, which is the fault, you are able to easily know the fault by applying this equation. So this is the fundamental reaction of acids and bases. We use this as the basis of discussing titration. This equation right here, we use it as the basis of discussing, sorry about that, as the basis of discussing titration, because it is the fundamental reaction of acids and bases. So if we write the general representation, like when we started the acid-base chemistry, we said that H plus OH will give you what? Water. Where H represents the acid because it is what is given out, and OH represents the base because it is what is receiving or accepting or taking. Thus, the idea behind a titration is the use of a known concentration of strong base to determine the concentration of weak acid. That is very key to note. So we have the idea, very key. This is what titration is basically about. The idea behind a titration is the use of a known concentration of a strong base, which represents your OH minus, to determine the concentration of weak acid, determine the concentration of the weak acid. So you try to figure out something here by using what is available, what is given, or what is already known based on the reaction that you know, and there you begin to apply the Heisenberg equation. So we are talking of, in this whole definition, as it were, use of a known concentration of a strong base to determine the concentration of weak acid. We are actually talking about the titration of a weak acid with a strong base. So the whole of this here actually implies, okay, so the whole of this here actually implies the titration of a weak acid with a strong base, period. The titration, it implies the titration of a weak acid weak acid, okay, with a strong base, with a strong base. Great. So that's basically it. So you want to do a titration of a strong acid, and you you can do a titration of a strong acid and a strong base, but a weak acid with a you can actually do a titration of a strong acid and a strong base, a weak acid with a weak base. However, the titration of a weak acid and a strong base is the most common titration that is carried out most often. So this type of titration is very common. So it's most common type of titration. A weak acid and a strong base, most common type of titration. All right, so OH here reacts with any hydrogen ion, either free or attached to an electronegative atom, either oxygen or nitrogen. So whether the OH is attached to oxygen or nitrogen, the OH will actually react with, sorry, whether the hydrogen is attached to nitrogen or oxygen, the OH will actually react to with any proton, with any H plus, any hydrogen in solution. Okay, so in other words, if the H plus is freely floating around in solution, the OH will grab it. That means it will accept it or collect it and turn it into water. And if it is attached to a nitrogen or oxygen, the OH is still going to rip off the hydrogen ion concentration away and turn it into water, leaving the negative charge behind. And when that happens, we'll look at an example is acetic acid solution. We'll take that in the next slide. So let's let me do this back and believe. So let's look at an acetic acid solution. An acetic acid solution. Okay, so acetic acid can generally be represented by ACOH minus, which is acetic known as your what? Acetate. All right, and the general structure for this is your CH3, C double bond O, O, then your H. So if you rip off this hydrogen ion, okay, what you have here is what? Your acetate. So this reaction takes place this reaction can take place as follows. So acetate above can take place as follows. So you have the reaction as this: OH plus what? Water in solution forward reaction because it is a weak acid, forward and backward reaction or reversible reaction. We have your hydrogen ion again plus what? Your CO minus. And this from the structure is what we know as your acetate. And of course, this is what? Your weak acid. Okay, so if we do the dissociation, acid dissociation constant of the following reaction equation, what we have is hydrogen ion concentration, hydrogen ion over concentration, acetate, okay, over your what? Weak acid, ACO minus. Remember that we said recall that we said H3O plus is same as H plus. So the value of the Ka is very small. Now this acetate reaction has a general dissociation constant of 1.75 times 10 raised to power minus 5, which is very, very small. So the value of the Ka is very small, and that shows that not very much of this reactant here, not very much of this reactant here is what is actually dissociated. A very little amount of it actually comes apart or gets dissociated, and much of the product is in the reactant form. So much of this product is in the reactant form. So as we continue to add OH minus to this solution, the fundamental reaction takes place. Remember, in titration, you add the base. As you continue to add OH minus, the fundamental reaction, which is, excuse me, your titration reaction takes place. So if you add OH minus, which represents your base, to your acid, which was not fully dissociated, if you add it, what you have left is this OH will rip off the hydrogen ion attached to this acetic acid to form what? Water. And what you have left is your ACO minus. So this is more like a neutralization reaction. So you have just like a quick illustration, you have something like this, and you have your ACOH, ACOH in solution. Okay, you have your ACOH. Okay, you have H plus, which is just that weak dissociation, and CO minus. Okay, and of course you have HCOH. So in this reversible reaction product, what you get, very little of the acid was dissociated to H plus and what? OH minus. So more of the concentration and the amount is still in the weak acid form. It's not fully dissociated. Hence, the Ka value is actually very small. So the whole of this as it is, that is what titration is. That is titration. As such, you add more of this OH, you are converting more of the acetic acid to acetate. As you continue to add OH to this, you continue to have that OH ripping off these hydrogens attached here and having more of the acetate. So that's basically what titration reaction is about. So you continue that until you have a significant amount of your acetate and what? Your acetic acid. A significant amount of your acetate by ripping away that hydrogen. So That's basically what happens here in this reaction here, as illustrated here. That is what is happening here. As you continue to add your OH, you have the ripping off of hydrogen. So in our next slide, we want to relate this to our Henderson-Hezibach equation. Next slide. Recall the Henderson-Hezibach equation. Recall the Henderson-Hezibach equation. You have pH is equal to pKa plus the log of your acetate with respect to that equation over your what? Acid, which is COH. So when enough of the OH has been added to convert exactly half of the of this, to convert exactly half of the weak acid to acetate, okay, then you have the concentration of this acid equaling the concentration of your what? The acetate. So very important to know that it's at that point that it represents your titration. So note, when enough OH minus, which represents your base, has been added to convert half of the acid to acetate, to convert half of what? The acid, to convert half of the acid, in this case you have CO, okay, to convert half of this acid to acetate, okay, which is your ACO minus. Then you have the concentration. Of the acid is equal to the concentration of what? The acetate. So at this point, we will want to write out the pH equation again. At this point, you have pH is equal to your pKa plus log ACO minus over, log concentration ACO minus your acetate over ACOH, which is your weak acid. Okay, so when you have this, okay, it's just like you have 1 mole of the acid, for instance, and you keep adding your OH, and you are able to now rip off the hydrogen on the acid to the extent that you have half of, instead of 1 mole, you have half of the concentration now is now half of the acid and half of the acetate. So when you have that, what you have is your, at this point you have your concentration ACO minus over your concentration ACOH. So at that half, what you have is equal to 1 because your concentration are now equal. So whatever is equal, it cancels out to give you 1. All right. And if you take this one and put it in this equation, what you now have is pH is equal to pKa plus log reading 1. And we all know that logarithm 1 is equal to what? 0. So what that implies is that pH is equal to pKa. pH is equal to pKa. This is exactly what titration represents. So this represents titration. So we have an experimental procedure, a very easy experimental procedure for determining pKa or Ka, either in pure chemistry. But equationally, we have shown that if it is titration, your pH is equal to your pKa. So in the next set of lectures, we'll begin to look at your titration curve to show how pH and pKa can be addressed. See you in the next class.